The room is quiet now, the kind of quiet that makes you notice your own breathing. Slow, soft, a small tide moving in and out. In the dark, everything feels gentle, like the universe has dimmed its lights for the night. Somewhere out there, clouds of dust and gas drift like sleep itself, folding, unfurling, changing shape in ways we barely understand. Matter isn't always what it seems. Sometimes it flows, sometimes it freezes, sometimes it hums in strange in-between states, like dreams caught halfway between worlds. I like to think the cosmos is still experimenting, still finding new ways to be solid and soft, light and hidden. Maybe we can listen to it together tonight. If your heart says yes, a quiet like and a soft subscribe would be lovely. For now, settle in, let your shoulders drop, close your eyes if it feels good. We'll begin together, unhurried and warm. What is a solid, really? The question sounds simple, like a stone resting in your palm. A solid keeps its shape. It doesn't pour. It doesn't slip away unless you press hard and mean it. A rock, a chair, a spoon, each one obliges, steady and familiar. Yet if you sit with the thought in a quiet room, it begins to soften at the edges. The idea that matter lives in just 3 tidy boxes, solid, liquid, gas, works the way a bedtime sketch works. Enough to see the outline, not enough to catch all the folds. Useful, yes. Complete, not quite. In the picture many of us learned, solids are rigid with a fixed shape and volume. Liquids keep their volume but relax their shape, sloshing to fill a cup's curve. Gases drift and spread, filling whatever space they're given. It's a comforting trio, like 3 notes that make a chord you can hum without thinking. Ice, water, steam, the same substance. 3 moods, for cooking, for classroom diagrams, for the everyday, that music plays well. Yet matter is not only a kitchen companion and a schoolhouse guest. It is the quiet machinery of stars and stones and skin, and it refuses to live forever inside simple lines. Look closer at what we casually call solid, and the neatness loosens. Many solids do arrange themselves into repeating patterns, tiny cities of atoms, each one knowing its corner, its angle, its neighbor. Salt does this. Diamond does this with a severity that turns carbon into light's favorite dance floor. But some solids don't stack so politely. Glass, obsidian, certain plastics, even the frozen sugar glinting in candy. All of them are what we call amorphous. Their atoms sit like a crowd that stopped moving mid-sentence. The room has gone quiet, but no one lined up. These materials look and feel solid. They tap back with a clink. Yet, underneath, their order is more like a moment of liquid that never quite became a crystal. Not chaos, exactly more a hush without a grid. That is a clue worth holding gently. Solid is often a behavior we witness, not a permanent identity. A behavior can last a breath or a century. It can depend on the temperature in the room, on how much weight you place, or on how patiently you watch. Take pitch, the dark, tar-like material that seems as firm as a paperweight. At a glance, it is stubborn. Knock it with a finger, and it behaves like a stone. Leave it alone for years, and it remembers how to flow. What looks like certainty becomes patience in disguise. Even the friendly shore between liquid and gas is not a clean edge. Heat a liquid the right way while confining it under pressure, and it reaches a supercritical state, a liminal hush where it flows like a gas and dissolves like a liquid. No sharp boundary, no tidy line across the map. The chart we grew up with starts to look less like 3 boxes and more like weather fronts and gradients, transition zones, where one quality thickens into another. The universe favors continuity, where our minds prefer doors. If you warm things enough, new personalities appear. If you cool them enough, the same. Plasmas, those seas of charged particles that make lightning crack and the sun burn, are sometimes called the fourth state of matter. Not exotic at all, really. They light street signs and hum in fluorescent lamps. Under pressure, materials can shed one structure and adopt another as calmly as a tree changing its leaves. Magnetic fields and electric currents can coax hidden orders to the surface. Phases, then, are the ways matter chooses to be with itself, guided by energy and crowding, by temperature and pressure, yet not only by those. In the small, quantum rules place their own requests, and the dance steps change. It helps to shift our attention from the boxes to the crossings. Phase transitions are where the story breathes out loud. Melting, freezing, boiling, condensing. The familiar names are really shorthand for molecules renegotiating their relationships. They jostle, more or less. They consent to stand in rows, or they refuse and drift. Properties flip. Brittle learns to be slippery. Soft learns to hold. You can see a tiny theater of this when you breathe on a winter morning. The water vapor you carry inside you, unseen, meets colder air and gathers into tiny droplets. For a heartbeat, your breath becomes a mist and then vanishes back into invisibility. A transition caught in flight, a little lesson offered free. Our trio of solid liquid gas is like the sea's surface on a calm day, honest but incomplete. Beneath that surface, currents wander, layers shift, warmth slides under coolness, and creatures move in patterns we only glimpse. Matter does much the same. Sometimes it lines up obediently. Sometimes it prefers a looser arrangement. Sometimes it ignores both and invents a pattern we didn't think to include. Nature owes us no simplicity. What it offers, instead, is consistency rules that hold, even when the outcomes surprise us. And those rules are written in a script we learn slowly, like learning to read by lamplight. This is why the comfort we take from the word solid belongs to our feelings more than to the atoms. In the quiet interior of matter, solidity is often a question of time. Wait long enough. Change the pressure gently. Nudge the temperature by a few careful degrees. What seemed firm can begin to creep. What seemed formless can suddenly decide to lock arms and stand. We recognize ourselves here. We hold together. We flow. We change when circumstances do. We discover, now and then, a state without a proper name, and we live in it until someone finds words. In that spirit, the story of glass returns like a rumor told in soft voices around old windows. You might have heard it, that the warped, wavy panes in centuries-old churches are thicker at the bottom because the glass flowed there, a slow-motion sag over time. Proof that glass is not truly solid but merely a liquid caught in a long sigh. It is a graceful picture, gravity making a poem out of patience. Yet the grace hides a misunderstanding. Glass at room temperature does not flow in any way we could measure across a human lifetime, or even across the span of recorded history. If it did, the thickening would always be at the bottom, and it is not. Sometimes the heavy edge sits at the top, or along a side. The truth is more practical. Older ways of making flat glass, spinning a crown, blowing a cylinder, and then flattening it, left sheets uneven. When builders set them into place, they often turned the thicker edge downward for stability. Sensible hands, not melting centuries. Does that mean the whisper was pointless? Not at all. There is something real behind it. Glass is an amorphous solid, which is to say its atoms are arranged like a cooled liquid that never settled into the marching order of a crystal. Quartz, its crystalline cousin, lays its atoms in tidy, repeating motifs. Glass declines that invitation. Imagine a ballroom where the music slowed and the dancers, mid-turn, fell asleep where they stood. No lines, no grid, just stillness with the memory of motion. The atoms in glass vibrate in place, as atoms in other solids do, but they never click into a repeating pattern. This gives glass some of its gifts: transparency that forgives small imperfections, hardness under the hand, and a way of carrying light that feels clean. This in-between quality has a gentle name: the glass transition. Unlike the clean snap of melting where a crystal yields at a definite temperature, the path into glass is a long slope. As a hot melt cools, molecular rearrangements slow, then slow again, until without a single trumpet the material seems frozen. No bright line to point at, only a deepening quiet. Yet at furnace heat, glass is honestly liquid. Gather it on a rod, blow a bubble, draw a ribbon. The movement is real honey-like, only fiercer, and the old tale of flowing windows belongs to the workshop, not the cathedral. The same lesson in patience appears in pitch, the dark cousin in this story. Brittle to a tap, but under gravity's small hand, it sighs. In a quiet experiment begun in 1927, a lump of pitch in a glass funnel has let fall a single drop. Only every 8 to 13 years change so slow you can share a decade with it and still miss the instant of letting go. Seen in that light, pitch never stops. It simply flows on a clock our eyes can't keep. And that long patience isn't pitches alone. Given the right stress and enough time, certain plastics and even some metals creep too, not pouring from a cup or rippling under a fingertip, but shifting molecule by molecule, like a breath that takes years. They don't fit neatly inside the tidy boxes we learned as children. They blur the line between fluid and solid and remind us that state often depends on the time scale we choose to notice. Obsidian sits with the amorphous family as if it has always belonged. Lava cooled too quickly to arrange itself into crystals leaves behind a glassy black that breaks in clean, curved shells, conchoidal fractures, sharp as a promise. It feels decisively solid and can take an edge fine enough for a surgeon, yet its inner arrangement never finished the crystal choreography. Think of a crowded room where conversation stopped mid-word and everyone fell still in the exact positions they held. No grid, no repeating motif, only quiet, suspended motion. Nature doesn't mind skipping the crystal step when she's in a hurry. These materials challenge our instincts in a gentle way. We trust what the hand and ear report. If it clinks when tapped, shatters when dropped, resists a thumb's push, it must be solid. But atoms don't care what we call them. They follow the book of motion and energy and arrangement. When those rules gather a material into a region between categories, when bonds hold enough to keep shape, yet relax enough to creep, we meet behaviors that are neither and both. Amorphous solids carry a quiet elegance, stillness that isn't entirely still, a structure that never declared itself finished. A window pane, a shard of obsidian, a funnel of pitch, taking a decade to let go each one, is a small lesson in how the universe can pause in between without being confused. It helps to see glass not as a stubborn liquid pretending to be solid, but as a different kind of order, one that makes room for disorder without apology. In a world that favors sharp borders and neat labels, glass offers a softer truth. Matter, like time, can slip between lines. That slipping isn't failure. It's another valid way to be. Ask most people to list the states of matter, and you'll hear the old trio: solid, liquid, gas. Sometimes someone adds, almost sheepishly, and plasma? That voice is right to speak up. Plasma is the cousin who moved away and quietly became the most visible relative of all. In the cosmos we can see, plasma is everywhere. Stars are oceans of it. The sun is a glowing testament to it. The faint veils and pillars in nebulae are traced by it. Even the auroras that ripple over Earth's poles are painted by it, thin and luminous, like silk caught on a magnetic wind. In simple terms, plasma is ionized gas. Add enough energy, heat, or voltage, and electrons slip their atomic leashes. The calm balance of equal protons and electrons gives way to a sea of positive ions, mingled with free electrons, buzzing and colliding, and responding to electric and magnetic fields as eagerly as a flock turns to a shift in air. That little break in balance changes everything. Plasma conducts electricity, shapes and is shaped by magnetic fields, and hosts waves, filaments, and spirals that drift and coil across astonishing distances. We don't see plasma often in daily life, which may be why it's easy to forget, but it's not hiding. Lightning is a brief, bright ribbon of plasma. The sun's surface is a calmer sea of it, by comparison, though no less grand. Neon signs and fluorescent bulbs call on plasma, too. Ionized gas inside a tube, excited by electricity, settling down by releasing light. That buzz you remember from an old storefront isn't only a sound, it's a chorus of particles gaining and giving back energy. Plasma's strangeness lives in how it answers to forces. Ordinary gases drift indifferently. Plasma is attentive. With magnetic fields, you can bend it, guide it, confine it. In laboratories, scientists try to hold plasma inside donut-shaped chambers called tokamaks, coaxing charged particles into a steady, contained dance so fusion reactions can warm the future. It's an attempt to hold lightning in a net woven from magnetism, a delicate art carried by robust machines. Nature's own galleries of plasma are generous. The northern and southern lights unfurl when charged particles from the solar wind follow Earth's magnetic field toward the poles and meet atoms in the upper air. Oxygen glows green most often. Nitrogen adds purples and reds. Excited and then calmed, the atoms give out light as they relax, and the sky becomes a curtain breathing in color. The same physics paints larger, louder scenes. Solar flares and coronal mass ejections, eruptions flung from the sun's atmosphere, send waves of plasma across the solar system. When those waves reach Earth, satellites can stumble, power grids can strain, and auroras can brighten. It's as if the sun sneezes and the whole neighborhood feels the ripple. Beyond our star, plasma fills the space between stars and even between galaxies. The arms of spirals glow in it. Ionized clouds in nebulae bloom because of it. If you could tally the atoms in the observable universe and ask, "What state are you in?" the great majority would answer, "Plasma." The universe seems to enjoy being electrified. Plasma is not only spectacle, it is practical and precise. A torch of plasma can cut steel as if it were pastry. Ion thrusters, which accelerate charged particles into quiet, persistent plumes, promise efficient paths for spacecraft. In hospitals and workshops, controlled plasma sterilizes instruments and etches surfaces at microscopic scales. Science fiction becomes quiet routine in clean rooms and engine bays. Yet plasma keeps its riddles. It doesn't obey the quick rules we lean on for solids, liquids, and gases. It has rhythms that can knot and kink, instabilities that can balloon or settle. Magnetic reconnection, the moment when magnetic field lines break and rejoin, can release sudden, immense energy and is thought to power solar flares and similar fireworks. Even our sun carries a puzzle with plasma at its heart. The surface simmers at roughly 6,000 degrees, but the corona lofted above it reaches into the millions. Why the outermost layer is so much hotter remains a question, with answers still arriving slowly, like dawn light moving across a room. All of this nudges us toward a more flexible view. Adding energy doesn't only make something warmer, it can shift the rulebook. A gas doesn't simply become a more excitable gas. With enough energy, it becomes plasma, a medium that listens to fields, carries currents, and builds luminous filaments that can stretch for light years. Matter isn't a staircase of 4 tidy steps. It's a set of neighborhoods with roads between them, and each neighborhood has its own customs. Now, gently change the weather. Picture gathering a small cloud of atoms and cooling them down, then down again. Colder until motion that once felt busy becomes almost a memory. Approach the coldest limit nature allows, that deep hush we call absolute zero, and watch what emerges. The atoms, once individuals with their own small agendas, begin to behave as if they are one. Not metaphorically, not working together the way we might say of friends, but literally entering a single shared quantum state, their separate identities fading into a common wave. The system acts like one extended, unified object. This is the Bose-Einstein condensate, a state of matter that sounds like a formal introduction but feels, in spirit, like a lullaby, where many voices blend until you hear only one smooth tone. In the quantum world, particles carry a dual nature, behaving like both little localized entities and waves spread in space. Each atom has a wave function, a soft, mathematical hush that describes the probabilities of where it might be and how it might move. At ordinary temperatures, these wave functions overlap and jostle like ripples across a pond stirred by many stones. The patterns interfere and scatter. No single rhythm dominates. As the system cools, the agitation quiets. The wave functions widen, like notes held longer, reaching farther. The ripples stop competing and begin to merge. Slowly, then decisively, the many becomes one. You no longer have a set of isolated players trading lines. You have a single, extended wave filling the stage. Position and momentum, once lively with uncertainty, settle into a shared arrangement, and the whole cloud begins to move as if it were a single, soft-bodied thing. From far away, this is just another phase change, like melting or freezing, but inverted, using stillness instead of heat. Up close, it is a change in logic. The boundaries between atoms soften until they are less like walls and more like curtains, and the system's behavior is dictated by the long, calm coherence of a collective wave. In laboratories, reaching this state requires care and patience, and light used as a kind of cooling hand. But the idea is spare and beautiful, cool enough, and individuality yields to chorus. There's a soft symmetry to how these stories fit. At one end, gas gains energy and ionizes into plasma, taking its cues from electric and magnetic fields glowing, braiding, carrying weather across a star. At the other, gas is calmed toward absolute zero until a condensate emerges, motion settling into a single, shared line. Between those poles live the familiar and the hesitant, solids and liquids, glasses that never quite chose, metals and plastics that creep when the clock runs long. The pattern underneath is steady. Matter isn't a set of boxes, it's a repertoire, and what it performs depends on energy, crowding, and time. From pitch that needs a decade to let go of one drop, to neon singing in a tube, each shift is less a disruption than a new rhythm taking the lead. Follow that rhythm into the cold, and a gentle distinction starts to matter. Some particles will share, some won't. The sharers are bosons, named for Satyendra Nath Bose, permitted to occupy the very same quantum state. Their stricter cousins, fermions, obey Pauli's rule and keep their distance. Lower the temperature, and the wave functions of bosons widen and overlap. Hush the noise further, and overlap stops being the exception and becomes the rule. The crowd ceases to be a crowd, and a many becomes one, setting the stage for a condensate to take its long, single note. At a low enough temperature, the distinction between this atom and that atom fades. It isn't that the particles bunch up like peas in a pod, it's that they become indistinguishable in the deepest sense. They behave as one extensive quantum object, a single shared state that fills the trap like a calm note filling a room. In the 1,920 seconds, Bose and Albert Einstein sketched this idea on paper and showed that nature would allow such a thing. The math sang quietly but clearly. The instruments to make the music in a lab did not yet exist. 70 years passed. Then, in the mid-1990 seconds, careful hands and patient light brought the prediction to life. Using lasers as cooling fingers and magnetic traps as cradles, researchers calmed a cloud of rubidium atoms to temperatures just a few billionths of a degree above absolute zero. The atoms' separate wave functions swelled and merged. A delicate shape appeared in the data, a sudden sharpening, a narrow spike signaling the birth of a Bose-Einstein condensate. A theory, held gently for decades, had found its body. Once atoms enter this condensate, they move with a shared intention. Nudge one region, and the whole responds, the way a single jellyfish ripples when touched, or a sheet lifts everywhere when you raise one corner. The collective motion overwhelms the individual fidgets. Out of that unity spill, effects that feel like magic, until you remember the rules have simply changed. A condensate can flow without friction, superfluidity. It can refuse the ordinary leaks and losses that slow other fluids, slipping along pathways that would stop anything else. It moves like a whisper, made of matter. What was once a chalkboard topic became a visible, hold-your-breath presence. In these ultra-cold clouds, laboratory lights can catch wave-like behavior at human scales. One famous demonstration split a condensate into two and then let them expand into each other. Where they overlapped, the density formed bright and dim stripes, interference patterns, the unmistakable signature of waves crossing. Not water waves, not beams of light. Atoms, whole atoms, acting like light in a double-slit experiment, written with matter itself. It was as if nature peeled back a layer to show that the wave-like possibility we speak of in whispers is willing to stand in the open, given enough cold. Making a condensate is not a matter of placing a gas in a freezer and waiting. Absolute zero, no thermal motion left to give lies at the end of a road we approach but never quite reach. So experimenters build a slope, First, laser cooling. Beams tuned to steal a little momentum each time an atom tries to move the wrong way, coaxing the cloud into slowness. Then, evaporative cooling. Let the hottest atoms escape, and the rest settle into a calmer average, just as a crowded room grows quieter when the loudest voices leave. Step by step, the motion shrinks until coherence can take hold. When it does, the system is fragile. A whisper of heat, a stray vibration, and the long note breaks back into many small sounds. But while it lasts, we see the quantum world drawn large enough to lean in and notice. There's a soft kind of poetry in the fact that this state appears only when energy is drained away. As randomness fades and motion subsides, order of a new sort takes the stage. Coherence grows out of quiet. The cold becomes not a lack, but a pattern. The way snowfall turns a tangled yard into a smooth field. Bose-Einstein condensates give us a tabletop for questions that once lived only in equations. We can watch tunneling and interference, measure phase and coherence, and study quantum phase transitions in slow motion. We can use these gentle systems to model early universe behaviors, or to imitate, in careful analogs, the horizons and flows that theory places around black holes. The strangest corners of physics come within arm's reach, safer, smaller, but still true to their logic. All of it began because someone asked how light would behave if its quanta were truly indistinguishable, and someone else saw that the same thinking might apply to matter. Bose's work with photons lit the path. Einstein widened it to atoms. Decades later, lasers and patience did the walking. The result is a new register in nature's music. If solids, liquids, and gases are the notes we hum in daylight, a condensate is the deep tone that appears when the room goes still and the mind grows unhurried. It reminds us that matter has more to say when it isn't busy, and that atoms, when asked kindly, can whisper together. Now imagine a liquid that ignores the brakes. You pour it, and it glides without drag. Set it spinning, and it keeps circling without loss, as though friction had forgotten to attend. Heat it a touch in just the right way, and it can climb a capillary tube and fountain out. Tilt the bowl, and it doesn't slosh so much as rearrange, selecting a motion that costs it nothing. This is the world of superfluids, fluids with essentially zero viscosity, no internal resistance at all. In everyday terms, viscosity is what makes honey slow and syrup thick. Even water pushes back a little when you stir it. A superfluid does not. Start it moving in a loop, and, in the absence of disturbance, it can flow for hours, days, even years, without measurable decay. The most famous example is helium, 4 cooled below about 2.17 Kelvin, a point called the lambda transition. Above that, liquid helium is unusual but familiar. Below it, the liquid becomes helium-2, a clear, quiet substance with behavior so unlike ordinary fluids that early researchers had to invent a new language to describe it. One of its signatures is the fountain effect. Insert a tiny capillary into a bath of superfluid helium and warm that capillary slightly. Instead of behaving like a normal fluid responding to pressure, the superfluid climbs and jets driven by differences in quantum energy rather than by the usual pushes and pulls. Another is the thin film that creeps, a layer of helium that crawls up the walls of its container and spills over the rim, a sheen called Rowland film. Gravity does not forbid it. Surface tension does not tame it. The rules at this temperature are written elsewhere. Underneath these oddities, is the same chorus we met in the condensate. Helium, 4 atoms are bosons, and at very low temperatures, a large fraction of them occupy a common quantum state. The liquid acts coherently. Motion becomes quantized, allowed only in specific, neat packages, and dissipation is avoided. Stir an ordinary liquid, and you get a messy cascade of swirls that break into smaller swirls and then into heat. Stir a superfluid, and you get tiny, orderly whirlpools, quantized vortices, each with a fixed, discrete amount of circulation. They don't fray into nothing. They keep their perfect rhythm, like dancers who never tire. Place superfluid helium in a torus, a donut-shaped container, and set it flowing. With no internal friction to slow it, that current can persist far beyond ordinary expectations. The image is simple, a ring and a flow, and yet the meaning is deep. The fluid has shifted from many small motions to a single global motion that the system sustains without paying a toll to entropy, provided you protect it from stray nudges. Helium-3 tells a different, more intricate story. Each helium-3 atom is a fermion, not a boson. It cannot share a quantum state the way helium-4 can. To become superfluid, helium-3 atoms must do something clever. Pair up. 2 fermions can form a composite that behaves, in effect, like a boson. Electrons in a superconductor do this, forming Cooper pairs that carry current without resistance. Helium-3 pairs in a similar spirit, but only at even lower temperatures, fractions of a Kelvin, above absolute zero, and the resulting superfluid has multiple distinct phases, each with its own internal symmetries and textures. It's as if helium-3 decided that one kind of perfection wasn't enough and composed a small catalog. The marvel of superfluidity rests on the same quiet foundation as the condensate: coherence. At one end of the energy spectrum, a gas heated and ionized becomes plasma and learns to listen to fields, to braid into luminous filaments across space. At the other end, a gas cooled to stillness merges into a condensate and learns to move as one, without friction, without loss. Superfluid helium is the liquid face of that same lesson. Push too hard and you break the spell. Protect the calm and the spell persists. In the lab, these states are fragile, but their meaning is sturdy. They let us study turbulence that comes in tidy quanta instead of chaotic splashes. They let us build sensors of exquisite sensitivity and clocks that keep time with long, even breaths. They let us test ideas about order born of quiet and motion born of rules. The techniques that bring them into being, laser cooling, magnetic trapping, evaporative thinning, are themselves a kind of lullaby, reducing motion until a new pattern can emerge. Bosons are free to gather. Fermions keep their distance unless they pair and, together, slip into the chorus. As temperature falls, wave functions broaden, overlap deepens, identity softens, and the system chooses unity. What was many becomes a shared phase that answers as one. In the lab, this looks undramatic. A rubidium cloud drifting a few billionths of a degree above absolute zero becomes a condensate. Helium-4 turns superfluid near 2.17 K. Helium-3 waits for even deeper cold to learn its delicate steps. Drain motion and coherence appears. Quiet the noise, and a new order speaks. You can watch it in a vacuum chamber or a polished loop where a liquid flows and never tires, proof that, given gentler conditions, matter prefers to sing in unison. And once you can hold coherence so calmly, a natural question arrives. Could that same effortless flow live inside a crystal's fixed pattern? That is the soft paradox of the supersolid. Imagine a material that remembers a lattice atoms in repeating ranks, and yet moves with the ease of a frictionless fluid. Shape and flow, side by side. For years, it was a rumor seen out of the corner of physics' eye, early hints in helium, beautiful but tangled in noise and competing explanations. The idea refused to settle until the tools did. Ultra-cold atoms, carefully tuned interactions, and sculpting light. In the 21st century, those steady hands coaxed matter into holding both truths at once, and the rumor stood still long enough to be measured. The recipe sounds like a lullaby sung to matter. Take a small cloud of atoms and cradle it in magnetic fields. Cool it until motion becomes a whisper. Then use lasers, not as heat, but as sculptors of interaction light that nudges how the atoms feel one another. Under the right balance, the cloud ripples into a crystal-like pattern, peaks and valleys of density repeating in space. At the very same moment, a coherent motion threads through the whole. The atoms know they are in formation, yet they glide, they move without leaving their places. It's like watching a floor of dancers hold formation while the entire pattern slides across the stage, never breaking rank. This behavior is born from a quiet conversation between quantum waves and mutual nudges. Each atom carries a wave nature, a soft presence spread in space. When many such waves overlap, they can interfere and form a standing pattern, bright here, dim there, repeating like the ribs of a lantern. That is the solid face. But because the waves also share a common rhythm, a phase that ties distant parts together, motion can pass through the grid without scattering. That is the superfluid face. Put together, you get a supersolid, order that breathes, structure with glide. Language strains a little under this. We are used to opposites, sitting far apart, rigid or flowing, still or moving. Supersolids remind us that nature writes in gradients and duets. Helium that fills a party balloon can, under deep cold and careful coaxing, carry flow without friction. Atoms that drift like a gas at room temperature can settle into a pattern that both holds and moves. The context, temperature, density, the gentleness of the trap decides which part of the repertoire shows. These states aren't just curiosities pressed like leaves between pages of theory. They offer ways to hold coherence motion with a shared phase long enough to study it. Superfluidity teaches us how to move energy without loss. Supersolidity hints at materials where structure and transport cooperate instead of compete. In quantum technologies, where keeping a fragile rhythm is everything, lessons from these calm regimes can help. Even if their devices remain delicate and cool, the principles echo outward to preserve the chorus, and the song carries far. There's a deeper comfort in watching matter choose these unlikely balances. A supersolid is proof that either or is sometimes both and, that a crystal lattice can host a river, that a river can remember its bed. Touch it too roughly, and it will break into ordinary pieces. Keep it sheltered, and the paradox stays intact, the way frost ferns keep their lacework if the window pane is left undisturbed. Much of physics feels like this at heart, not loud spectacle, but rules meeting conditions, and, in that meeting, a pattern unfolding. Now let the mind drift backward, as if rewinding a film until the first frames flicker into view, far before stars, before atoms, before protons and neutrons learned their names. In the first few microseconds after the Big Bang, the universe was so hot, so dense, so saturated with energy that anything like a familiar particle could not keep itself together. The world was a bright, roaring broth of more basic ingredients, quarks and gluons, moving free in a state called quark-gluon plasma. It was not a tidy kitchen, it was a furnace turned into a sea. Quarks are the small constituents that, later, would be bound into protons and neutrons. Gluons are the carriers of the strong force, the glue that binds quarks into snug bundles. Under normal conditions, quarks and gluons do not roam. Stretch the connection between quarks, and the force resists, like a stubborn elastic that only pulls harder. Try to separate them, and the energy you pour in simply spawns new bound pairs. But push the temperature to astonishing heights, trillions of degrees, and confinement eases. Bonds slacken, the particles roam, the soup appears. You might expect a chaos of hard knocks and random jolts, a gas that slams and scatters. Yet quark-gluon plasma does something gentler. It flows like an almost perfect liquid with extremely low viscosity. The hottest substance we know how to make turns out to be among the smoothest flowing. That is one of those turns of nature that feels like a smile fire becoming silk when seen at the right scale. Recreating this early universe moment on Earth takes machines the size of stories. At the relativistic Heavy Ion Collider in New York and at the Large Hadron Collider at CERN, heavy nuclei, gold or lead, are accelerated until they skim just shy of the speed of light. Then they meet head-on. For a breath shorter than a breath fractions of a microsecond, the energy density in the tiny overlap region climbs high enough to melt ordinary matter. Protons and neutrons lose their shape. Quarks and gluons spill free. A droplet of the first universe appears and begins to expand and cool. The droplet does not last. The strong force is patient and strong in the way deep roots are strong, overwhelming up close. As the fire fades, quarks are drawn back together, folded into protons, neutrons, and other short-lived hadrons. In that turning, a map is written in the way the droplet flows and freezes. By tracing how the liquid expanded, by measuring the directions and energies of the particles that emerge, physicists reconstruct the brief choreography, the pressure, the viscosity, the time it took to cool, like listening to the echo in a room to learn its shape. This line of work touches old questions with new fingertips. Our best theories say the Big Bang began with matter and antimatter in balance, mirror images in equal amounts. Yet the sky we inherit is made of matter. Somewhere, small asymmetries tipped the scales. Processes at energies like those inside the plasma, tiny differences in how particles and antiparticles behave, may have contributed to that gentle imbalance that let anything persist at all. If the symmetry had been perfect, the universe would have dissolved into light and left no atoms, no stars, no listeners for the night. The numbers attached to this are stark and beautiful. Experiments have produced plasmas reaching temperatures of several trillion degrees hotter than the core of any star, yet behaving with the grace of a near-perfect fluid. The time is brief, the size is minute, but the clarity is a gift. For a blink, a miniature past opens in a ring of magnets and steel, and then it is gone, leaving measurements like footprints in cooling ash. The story does not have to end at the collider. There are places in the cosmos where densities and pressures climb so high that matter is pressed into identities we only meet in equations. The interiors of neutron stars pack mass like a city packs stories. Gravity so intense that electrons and protons are squeezed into neutrons until the entire star is a giant nucleus. Some theories suggest that deeper still, in certain cores or during violent transitions, quarks may roam again, forming regions of deconfined matter. There are even speculations about quark stars, objects denser than neutron stars, where quarks are pooled into a sea. These remain ideas, not certainties, but the search is part of the same patient curiosity. Follow the rules to their edges and look over. Through all of this, gluons do steady work. They are not just messengers. They are the woven fabric of the strong force itself, binding quarks with a strength that dwarfs the electromagnetic pull at short range. In the plasma, at the highest energies, that binding loosens enough to let motion run free, let the energy fall, and the same force slams the door with no anger, only fidelity. An elastic stretched, an elastic released. It is humbling to realize that the protons and neutrons that build our bodies are condensed survivors, a cooler melody that formed as the original fire relaxed. We stroll comfortably at 20 degrees Celsius, while the matter that makes our blood and bones learned its first rules at temperatures louder than language. The family history of every atom includes a brief chapter written in heat and light we can barely imagine. The contrast with the ultra-cold isn't a clash, it's a harmony. At one edge, near absolute zero, atoms fall into step condensates, superfluids, supersolids, motion coherent and nearly without loss. At the other, at trillion-degree heights, bonds loosen into a quark-gluon tide that flows with astonishing smoothness before cooling back into familiar particles. High energy or low, the refrain holds. When conditions gather just so, matter finds elegant ways to move, either by sharing a single quiet phase, or by becoming so hot that even its fiercest ties relax into silk. Hold both scenes at once. In a cold chamber, a rippling lattice sliding without friction. In a bright collision, a first-moment droplet expanding with impossible grace, then settling into building blocks. Two edges of the same weave, rules rarely raising their voices, yet shaping stone, star, and breath alike. If the words feel stretched solids that glide, liquids at 1,000,000,000,000 degrees that flow like cloth, that's fine. Nature promised steadiness, not simple labels. One lesson shows structure and flow as partners. The other turns hottest chaos into the smoothest motion. Together they suggest a deeper continuity. Matter is not only what it is, but how it moves when the world around it changes. Seen up close, that hot edge has a name. Quark-gluon plasma lives and dies inside the flash of collisions, brief and hidden, but full of memory. In that short-lived glow is a record of how the universe cooled into patterns, how raw energy learned to sit down and become matter, how first turbulence softened into first order. It is our nearest portrait of the cosmos before it settled, an instant when everything was free, fast, impossibly hot parts not yet agreed, already rehearsing the shape of what would endure. The ingredients are tiny and fierce. Quarks, smaller pieces that will later make up protons and neutrons. Gluons, the carriers of the strong force. The glue that binds quarks into tight bundles. Under ordinary conditions, that force refuses to let quarks wander. Try to pull them apart, and the force pulls back harder. The way a stubborn elastic tightens as you stretch it. But lift the temperature to truly staggering heights, trillions of degrees, and the binding loosens. For a breath, quarks and gluons roam as a hot, bright liquid. It is the earliest kind of matter we can point to and say, here is what it felt like before structure. You might expect a stormy gas when bonds dissolve. Instead, this stuff flows with surprising grace, an almost perfect liquid with extraordinarily low viscosity. The hottest material we can make becomes one of the smoothest moving. There's a tender irony in that, fire acting like silk. To create it on Earth, we use giant rings of magnets to send heavy atomic nuclei, gold, lead flying nearly at light speed, and then, for an instant, let them meet head-on. In that overlap, for fractions of a microsecond, the energy density soars. The familiar architecture of protons and neutrons melts. A tiny drop of early universe liquid appears, expands, and cools. The drop can't last. As it relaxes, the strong force takes charge again. Quarks rejoin, pulled into hadrons, protons, and neutrons, among the first to reappear. Yet while the droplet lives, it leaves clues in the way it flows and freezes, in the patterns of particles flying outward as it cools. By catching those patterns, scientists can sketch the pressure, the temperature, the timing, a kind of echo mapping that turns a fleeting glow into a story with shape. That story may hold pieces of older puzzles. Our best equations say the Big Bang made matter and antimatter in equal measure. But the night around us is built from matter. The mirror didn't get half. Somewhere, tiny asymmetries nudged the balance. The behaviors at early universe energies, subtle differences in how particles and antiparticles move and transform, could have helped tip the scales, allowing matter to survive instead of vanishing in a clean flash of symmetry. Quark-gluon plasma doesn't give the whole answer, but it opens a window onto the part of the morning when such choices were possible. It is humbling to remember that the particles in our bones are, in a sense, cooled survivors of that earlier sea. We keep house at 20 degrees, but our fabric learned its first rules in a furnace bright enough to wash color out of language. The contrast with the ultra-cold is not a contradiction, it's a harmony. At one edge of the thermometer, extreme heat relaxes the strongest bonds and creates a near-perfect liquid. At the other, extreme cold invites coherence, turns many voices into one, and allows flow without loss. Both edges show a deeper pattern. When conditions are just so, matter finds elegant ways to move. Hold that thought of motion for a beat. Now picture a pendulum that swings forever without anyone winding it up. Not because energy is being secretly added, but because its swing itself is the lowest cost thing it can do. In the everyday world, that's fantasy. Friction and heat win. Perpetual motion belongs with hopeful sketches in old notebooks. Yet, in the quantum world, there is an idea, and now a reality, that rhymes with that dream, without breaking any rules: time crystals. The name sounds like it wandered in from a novel, but the concept is careful and real. Ordinary crystals repeat in space, walk through a diamond's lattice, and the pattern repeats, neat and steady. Sit the crystal in its lowest energy state, its ground state, and nothing changes with time. Stillness is the rule. A time crystal carries repetition not only in space but in time. Even in its lowest energy configuration, its internal state cycles, returning to itself with a steady rhythm, not gaining energy, not spending it. Just ticking, the way a pattern recurs in a song, even when the volume is almost silence. The proposal first appeared in 2012, when Frank Wilczek asked whether a system could break time translation symmetry the way ordinary crystals break spatial symmetry, could choose a repeating beat in time even when no external beat is forced upon it. Alarm bells rang at the mention of motion that doesn't die. But the idea wasn't a perpetual motion machine smuggling energy from nowhere. It was more delicate. Motion as an intrinsic, stable pattern of the ground state itself, protected by quantum rules and specific conditions. For a while, it lived as a question. Then experiments began to put shape to it, not as perfectly isolated, always ticking systems, but as quantum systems, nudged in the right way and refusing to heat up in the usual sense. In chains of trapped ions and in arrays of superconducting qubits, researchers drove the system with regular kicks and found a response at a different, stable rhythm, a subharmonic. Tap every 2 seconds. The system answers every 4. Keep tapping. It keeps the doubled beat without drifting. This persistence, this ability to lock into a rhythm that is not the driving rhythm and to hold it against noise, marks what we call a discrete time crystal. It helps to think of it as a careful balance. The system is driven, yes, but it doesn't absorb energy, like a drum that gets louder with every hit. Instead, disorder and interactions in the many-body system trap energy locally, a regime called many-body localization, so the drive sustains the rhythm without heating the whole. The pattern becomes a kind of protected loop. Even small imperfections and random bumps do not wash it out. It's not perpetual motion in the outlaw sense. It's motion held in place by symmetry and structure. Quantum processors have joined the story, too. On platforms like Google's Sycamore, researchers programmed sequences that flip and twist qubits in just the right cadence. The result is a state that flips back and forth at a fixed subharmonic tempo and resists decay across many cycles. Think of it as a quantum flipbook that keeps turning the same 2 pages forever without smudging the ink. It doesn't power a toaster or run a clock on your wall. It demonstrates that ground state and stillness are not synonyms when quantum rules have more to say. There's a philosophical sweetness to this. We often equate stability with rest. A crystal sits, a pendulum at the bottom hangs, but a time crystal offers a softer idea. Motion can be the stable thing. Repetition can be order. Change can be the constant. It reframes the word equilibrium from silence to rhythm, quiet movement that doesn't spend itself. That thought echoes the other states we've been visiting. Superfluids flow without friction, a motion that doesn't die out. Supersolids hold pattern and glide at once. Time crystals add another voice, motion without travel, a pulse rather than a flow, a regular change in internal configuration that holds its tune. All 3 teach us that matter's possibilities widen when we look past the old boxes and listen for behaviors that persist without loss. Practical uses will take time, and they may arrive sideways. What matters now is the new grammar they bring. In quantum technologies, where coherence is fragile and precious, states that resist certain kinds of noise are valuable. Time crystalline behavior may help us store or process quantum information more gently. Even if the devices remain small and cold, the lessons about protecting rhythm against disorder travel well. They hint that we can engineer systems in which a pattern maintains itself, not by fighting the environment, but by living in a symmetry the environment cannot easily break. It is easy to get carried away and imagine crystals of hours you can hold in your hand. Better to keep the wonder close and the image honest. Time crystals aren't made of time, and they won't show up in a rock shop. They are arrangements of matter and motion that repeat in time the way a lattice repeats in space. They expand our sense of what stable can mean. They remind us that the universe still keeps a few playful turns in reserve, ready for anyone patient enough to notice a rhythm where we expected a pause. Between the very hot liquid of the first moments and the very cold rhythms of the quantum lab, a theme keeps returning. When conditions favor a shared rule, low loss, strong symmetry, protected coherence, matter moves beautifully. Sometimes that beauty looks like silk made of fire. Sometimes it looks like a tick that never tires. Sometimes it looks like a flow that refuses to slow. Each one feels, at first, like a trick. Each one turns out to be a lesson in how rules, when tuned, can sustain motion without waste. If you lean back for a moment, you might hear how this descends into the everyday. Not all mysteries wear lab coats. Some sit on a kitchen shelf and pretend to be simple until you ask them to move. There's a kind of playful mischief in a thick sauce that won't budge, then suddenly runs. In a bottle you tap once, twice, and then finally everything slides. You tip, you coax, you wait, and nothing. Then, all at once, everything yields. The world of soft matter smiles at the same idea, that under gentle stresses and hidden rhythms, even the familiar decides to flow. Then, with a little more coaxing, the ketchup finally lets go and tumbles out in a single unruly glob. It isn't mischief for mischief's sake, though it can feel that way when your fries are waiting. Ketchup like toothpaste, slime, custard, yogurt, and a whole parade of everyday goos doesn't follow the tidy expectations we borrow from water. These are non-Newtonian fluids, materials that change their resistance to flow depending on how you touch them. They lean into a small truth the world keeps repeating. Matter is not a box, but a behavior. Sir Isaac Newton gifted us a simple picture for simple liquids. Viscosity, the measure of a fluid's internal resistance, stays the same no matter how hard you push. Water behaves that way. Pour it softly or stir it hard. Its texture doesn't thicken or thin because of your insistence. That's Newtonian comfort. Non-Newtonian fluids say, quietly, not tonight. Their viscosity depends on stress. Some grow thicker the harder you push. Some relax and become easier. Some feel solid until you poke. Some feel liquid until you squeeze. It's not magic, though it plays like a good card trick in the kitchen. It's structure choosing how to respond. Consider oobleck, a kitchen table wonder made from cornstarch and water. Move your spoon slowly, and it oozes, patient and obliging. Strike it, and it fights back, stiffening under your hand, even cracking if you hit just right. Fill a tray and run quickly across. Your feet bounce on what seems a solid floor. Stand still, and you sink. The secret lives in the cornstarch grains suspended in water. When motion is gentle, they have room to slip past one another, and the mixture flows. Under sudden force, they jam, pressed into fleeting contact networks that lock for a heartbeat, turning the pool into a temporary pavement. This is sheer thickening. The harder you push, the thicker it becomes. Picture a hallway full of people. Calm walking lets everyone slide by. A sprint makes the whole corridor seize. Ketchup does the opposite, a masterclass in sheer thinning. Left to itself, it's stubborn, clinging to glass like it means to stay. Tap and shake, and its internal microstructure loosens. Tomato fibers and polymer chains align and disentangle, and the sauce flows freely. Toothpaste and paint share the trick. On the shelf or in the tube, they don't run. Under a brush or between bristles, they spread like silk. We even design them that way, stable when idle, smooth when asked to move. It's a kindness disguised as convenience. Between thickening and thinning sits a family that blurs the line more deeply: viscoelastic materials. Slime is a friendly introduction. Pull slowly, and it stretches into long ribbons. Tug sharply, and it snaps. Set it down, and it can hold a shape for a while before relaxing into a puddle. Long polymer chains like tiny bowls of spaghetti, tangled and clinging, are the cause. Move gently, and the chains uncoil and slide. Move too quickly, and the tangles resist like springs and then bounce back, part liquid, part elastic, entirely entertaining. Gels are another soft compromise. They are mostly liquid, trapped in a sparse, solid-like network. Hair gel, gelatin desserts, the wobble on a plate. Water molecules are free to move, but they wander within corridors set by a microscopic scaffold, held together by chemical bonds or physical entanglements. The result is a substance that holds a shape, wobbles when nudged, and can melt back toward liquid under heat or time. Think of a dance where everyone is free to step, but only within the lines of the choreography. Amorphous solids belong in this gallery of in-between behavior. Unlike crystals, which repeat themselves neatly in space, amorphous materials lack long-range order. Their atoms settle like a crowd that stopped mid-conversation, stilled, but not lined up. Glass is the emblem, joined by plastics, waxes, and some rubbers. They don't flow like liquids, not for us, not in the minutes and hours we handle them. Yet, under heat, pressure, or merely long patience, they can sag, creep, and slowly rearrange. Solidity, in their case, is conditional, a promise kept for a time and a context. Even biology enlists non-Newtonian tricks. Blood is a complex fluid that becomes easier to move under higher shear, a kind of built-in shear thinning that helps it travel through narrow vessels where resistance would otherwise rise. Saliva, mucus, and egg whites also change their flow character under stress. They cushion, protect, and adapt precisely because their internal structures respond to touch. The body keeps its own rheology, its own understanding of flow tucked into every quiet motion. Part of the delight is how common and counterintuitive these materials are. They hide in plain sight. The shampoo that suddenly gushes when it first yields, the paint that refuses to drip but glides under a roller, the wet sand that firms under your step, each is a small negotiation between microstructure and force. The lesson is broader than a kitchen table. Response depends on how you ask. Engineers and scientists make use of this. Shear thickening fluids can live inside flexible fabrics to harden on impact, spreading and absorbing energy, light, comfortable, and surprisingly protective. Sports pads, helmets, and certain astronaut gear borrow the effect. In factories, non-Newtonian recipes tune flow rates, tame splatter, lay down coatings with precision, or build textures that simple liquids could never hold. In the lab, these materials teach us to connect structure to behavior. Rheology, the study of flow and deformation, uses them like mirrors, showing how internal architecture shapes the way a substance moves. The same ideas help model landslides and mudflows, study the slip of faults in earthquakes, and design foods that feel right on the tongue. They're fun, too. Smacking a bowl of oobleck to watch it stiffen, or folding a glossy slime until it shines, scratches an old human itch to test, to prod, to learn by feel. There's a sense in which these materials feel alive. They answer you. They push back differently when you push differently. They're playful teachers of a serious idea, that labels are less reliable than behaviors, that force and flow are a conversation, not a command. Keep that thought behavior over label as the story tilts from squish to shape. Take a donut and a coffee mug. At breakfast, they are not the same thing. In topology, they are twins. Each has one hole, and that count stays true under any gentle stretch or bend that doesn't tear or glue. Topology doesn't ask about sharp corners or smooth curves. It asks what survives distortion. That whimsical-sounding question turns out to reach deep into how matter can organize itself. In certain quantum systems, the defining properties aren't local patterns like atoms aligning into a crystal, but global features, how the system's wave functions twist and wrap through abstract spaces. This is the world of topological phases, where shape means the shape of allowed states, and where robustness comes not from stiffness, but from the way a pattern cannot be unwound without breaking it. If you've ever tried to undonut a donut without removing the hole, you know what protection by topology feels like. The modern story gathered momentum with the quantum Hall effect. Put a very clean, very thin sheet of electrons in a strong magnetic field at very low temperatures and measure how easily current slides sideways through it. Instead of changing smoothly as you tune the field, the conductance locks into plateaus, perfectly quantized steps, increasing by whole numbers with a precision that makes metrologists smile. Scratch the surface, add a smidge of disorder, warm it a pinch, the steps remain. The explanation lives in topology. The electron's quantum states wrap around the available space in a way counted by topological invariance, numbers that do not change under gentle deformations. As long as you don't tear the space by closing a crucial gap in the energy spectrum, the count holds, and so does the conductance. From that insight grew a family of materials that feel a little like paradoxes until you get used to them: topological insulators. In the interior, they behave like insulators. Electrons in the bulk don't flow easily. Along the edges or surfaces, they conduct with grace. Imagine a chocolate truffle that's quiet inside, but whose shell carries current as if it were a silver wire. Roughen the edge, dent the surface, swap a few atoms. So long as the system's topology stays the same, the edge conduction persists. It's not stubbornness, it's protection, born of shape in a space we don't see. This is different from the phases you learn first, which are often born from symmetry breaking. Water freezes and chooses a crystalline pattern. A magnet cools and the spins align. Topological phases can exist without such local choices. Their stability is global, a kind of holistic entanglement that resists ordinary noise. That makes them not only beautiful, but promising for quantum technologies. If information can be tied to a topological feature, something like a hole rather than a bump, it becomes harder for stray influences to spoil it. The system would need a tear, not a tug, to forget. In some topological settings, even the particles that seem to emerge are new in kind. In the fractional quantum Hall effect, the collective behavior of many electrons conspires to mimic charges that are fractions of an electron's charge. Nothing fundamental is being cut into pieces. Rather, the whole system organizes into excitations that carry a portion of the usual charge and obey unusual statistics. It's like a stadium wave. No single person runs laps, but the pattern moves as if it were a separate entity. The quasi-particles that ride these patterns can braid around one another, pick up phases, and return changed in ways that depend on the path. Not just the destination, a hint of information processing done by weaving rather than writing. The common thread through oobleck and ketchup, gels and glass, coffee mugs and donuts, Hall plateaus and edge currents, is not a taste for trivia, but a quiet insistence. Matter is richer than our first nouns for it. Sometimes the richness comes from microstructure that rearranges under stress. Sometimes it comes from global properties that no scratch can undo. Sometimes the knobs are temperature and pressure. Sometimes the handles are geometry and phase. In all cases, behavior tells the deeper truth. Walk back through the day with that in mind. The shampoo that thins in your hand, the paint that waits on the brush, the pane of glass that rings when flicked yet holds a disorder within, the sand firm underfoot in the wash of a wave. Then, down the hall of thought, a two-dimensional electron sea that counts in whole steps as you turn a knob, and a material whose edges sing while its middle stays hushed. None of these are mistakes. They are different answers to different conditions, stitched from the same rules. And if you tilt your ear a little, the differences begin to harmonize. Non-Newtonian fluids teach that flow depends on how and how fast you ask. Amorphous solids remind you that structure can be enough without a pattern. Topological phases show that some properties live in the way a system is knotted rather than in what it's made of. You can stretch one into another with patience and the right tools, cooling and heating, shaking and stilling, bending and confining, without ever leaving the language of physics. The lesson is patient and generous. Labels are useful, but they are not verdicts. The world answers gently to the way we touch it, from the ketchup bottle to the quiet edge of a quantum sea. And the answers, however strange, are steady once you learn to listen. Stranger still than quantized steps and singing edges are the particles that only truly exist in flatlands. Anyons live in two-dimensional systems and refuse the old categories. Swap two fermions like electrons, and their shared wave function flips sign. Swap two bosons like photons, and nothing changes. Swap two anyons, and the wave function can pick up a twist that is neither same nor flipped, a phase that remembers the path you took. Their behavior is braided into the topology of the space they inhabit. The story is not just who met whom, but how they wound around each other to get there. That winding is more than a curiosity. It is a promise. In topological quantum computing, information could be stored in the braids world lines of anyons, looping through time rather than in fragile local states. Nudge the system gently, and the braid remains. Only a tear in the fabric, a true topological change, can undo it. Errors that plague ordinary qubits fade in importance when the memory is tied to a knot rather than a number. The enchantment here is that you can't see any of this with a microscope. The atoms don't rearrange into a special quilt. The magic hides in mathematics, in how the quantum states twist and stitch through abstract dimensions. It's like learning your living room has a hidden door, not in the wall, but in the way your furniture quietly resonates with the room itself. This realm resists tidy tables. Topological phases don't fit neatly alongside solid, liquid, gas. They ask for a different chart, one that blends condensed matter, quantum theory, and pure geometry. Here, wave functions draw loops. Here, structure is defined not by where particles sit, but by what happens when you try to move them around each other. The shapes are global, holistic, and stubborn. In three-dimensional materials, the picture doesn't vanish, it deepens. Surface states can conduct only along particular faces, protected from backscattering by the system's topology. Magnetic textures can curl into skyramions, tiny whirlpools of spin that behave like particles and carry their own topological charge. You can jostle them, but to erase them, you have to unmake their knots. This robustness is the point. Ordinary conductors sulk when scratched. Topological ones shrug. Their key properties are baked into a pattern that small insults can't unweave, which is why they're so tempting for devices that must endure noise and disorder. Performance, here, is rooted not in perfection, but in the twisty logic of quantum geometry. Topology's reach is wider than electrons. Photons can be shepherded through carefully patterned structures so that light acquires topological protection, turning corners without reflections, sliding past defects without loss. That's topological photonics. Sound, too, can be given protected pathways, topological acoustics, guiding vibrations around obstacles, as if the air remembered a promise you made to it. Even mechanical lattices can hold modes that won't scatter away because the shape of their allowed motions is knotted in the right way. Wherever waves, fields, and geometry cross paths, topology can leave its signature. Underneath all these examples is a change in how we ask questions. Instead of, "What is this made of?" we ask, "How are its possibilities arranged?" Matter gains a memory, not bits on a chip, but a memory of twists and loops in an invisible space. It doesn't remember where it has been so much as how it moved. Resilience grows from relationships, not pieces. The universe seems to murmur that structure isn't only what we can see, but also how things connect, and that in those connections lie new ways of being. Now, lift your eyes to something you know by heart, a screen glowing in your hand, smooth, calm, full of color. It runs on one of the gentlest in-between states we've found, liquid crystal. The name sounds contradictory because the material is contradictory in a friendly way. Its molecules flow like a liquid, their centers of mass free to wander, yet they maintain an overall alignment, like a crystal, long, rod-like molecules pointing, on average, in the same direction. Picture dancers crossing a stage with freedom in their steps, but facing the same way, their orientation choreographed even as their positions change. That alignment is not a footnote. It's the trick that lets a display work with such small sips of power. In an LCD, thin films of liquid crystal sit between polarizers. Apply a voltage, and the molecules tilt. Change the tilt, and you change how the light's polarization twists as it passes. In tiny pixel regions, this decides whether light is blocked or allowed through. Images, letters, and colors are written by fields that gently turn molecular compasses. Millions of little needles pivot in concert, and your eyes see a city of pixels wake and sleep. The road to your pocket ran through a laboratory in a moment of confusion. In the late 1800s, Friedrich Reinitzer heated a substance derived from cholesterol and watched it turn cloudy instead of jumping cleanly from crystal to liquid. An intermediate phase lingered, neither one nor the other. Later work revealed the truth. A new class of states living between the usual categories. Scientists learned to sort these phases by how much order they kept. In the nematic phase, molecules align but don't form layers like matchsticks floating in water, all pointed roughly alike. In smectic phases, alignment comes with stacking. Molecules form sliding sheets, adding layer by layer order. In chiral nematic cholesteric phases, alignment twists gradually with depth, building a helical structure that reflects certain colors. That's why mood rings shimmer and thermochromic patches change hue with temperature. The pitch of the twist selects the light. Nature discovered liquid crystalline order long before we did. Cell membranes carry some of its logic layers with freedom within planes. Certain tissues in the eye rely on directional order without rigidity. The theme is balance, enough structure to hold function, enough freedom to move and respond. Because their orientation can be tuned by electric or magnetic fields, liquid crystals are energy thrifty. Small nudges shift large optical effects. The same property makes them useful beyond screens, in tunable lenses, filters, and lab instruments where light must be steered quietly. There's a quiet loveliness in how they behave. Watch under polarized light and you'll see textures that look like threads and rivers, domains rotating into place, defects sliding like tiny commas across a page. They convey a lesson about moderation, that you can hold a form without clutching it, and you can move without losing grace. The story hasn't stopped at televisions and watches. Researchers are shaping liquid crystals for soft robotics, where motion can come from fields and heat rather than gears, for sensors that change optical response to trace chemicals or strain, for scaffolds that guide growth and healing in tissues that prefer a directional cue. Each molecule's tilt carries information about force, temperature, and surrounding fields. Together, they form communities of orientation, sensitive and self-correcting in a way that feels almost aware. If all this feels pleasantly in between, water will happily complicate it further with its own multiple lives in solid form. Ice in daily life seems like the simplest thing. It clinks and cracks, cools a glass, frosts a window, yet ice is a family name. Under different pressures and temperatures, water's molecules can stack in many architectures. At least 19 crystalline varieties have been identified so far, and theory sketches more. Even the familiar ice that dusts a winter morning ice is special. The H stands for hexagonal, a lattice with six-fold symmetry. That geometry spreads molecules farther apart than in liquid water, so ice floats. Most materials become denser when they freeze. Water keeps making exceptions and saving lakes. Step away from the narrow comfort of sea-level cold and the blueprints change. Turn the pressure knob upward, chill more deeply, or do both, and water's hydrogen bonds strike new bargains. Roman numerals mark the designs: 2, 3, V, 7, and onward. Some are denser, with more compact arrangements. Some rearrange hydrogen ordering. Some form cubic patterns instead of hexagonal. It is as if the same poem is rewritten in different meters depending on how firmly you press the page. Planets and moons hold these phases in their mantles and cores. On Earth, a diamond anvil cell can coax them into brief existence, while X-rays read their structures. There is a thread here: topologies, hidden knots, anions, braids, liquid crystals, poised alignment, ices, many scripts that doesn't demand attention but rewards it. Again and again, matter shows that categories are bridges, not walls. Anions teach that identity can depend on the path. Topological phases teach that protection can be woven into shape rather than stitched onto place. Liquid crystals teach that order can travel with flow. Ice teaches that even the ordinary hides a parliament of possibilities, waiting for a change in context. Walk your mind back over the scenes. A flat electron sea that remembers loops. Braids that store a qubit like a knot stores a story. A sheet of molecules pivoting to draw a letter of light. A hexagon that keeps ice afloat, and 19 cousins that appear when the world squeezes. None of this is loud. All of it is steady. It suggests a kinder way to think about matter, not as a list of things, but as a library of ways to be some robust because of geometry, some gentle because of balance, some surprising because of pressure or heat. When the world asks for a rhythm rather than a pose, these states answer. And as your screen dims, you are, quite literally, watching liquid crystals relax their alignment, pixels folding into darkness as fields release. Somewhere, a lab ring sends ions on another lap, and a two-dimensional gas traces another perfect step. Somewhere else, an anvil tightens, and a new ice flickers into being long enough for a measurement and a smile. The universe keeps these quiet rooms open, places where form and flow bargain with each other and settle into something graceful. If you listen softly, you can hear how the bargain is struck, not by force, but by the shape of possibilities, and by the gentle insistence that even opposites can share a page. Some kinds of ice are packed tight, some a little looser, and some arrange themselves with symmetries so peculiar you'd think a hurried architect dreamed them after too much sugar. Ice, too, for instance, appears under higher pressure and tucks its molecules into a skewed, rhombohedral pattern, like a box pinched gently until its angles lean, push harder, and other blueprints arrive. Ice V and Ice VI accept the squeeze and stack water in closer, more intimate configurations, each design a different way to balance the pull of hydrogen bonds with the press of the world around it. Ice 7 is the celebrity of the deep. It forms at high pressures and can endure high temperatures too. The kind of ice you'd expect in the mantles of large icy moons and water-rich exoplanets, dense, strong, and quietly alien. It could be growing now beneath Europa's cracked skin or inside a super-Earth where heat and weight share the stage. There is also Ice XI, a ferroelectric phase. Its molecular dipoles tilt in agreement, aligning into a shared direction so the crystal keeps a tiny internal electric field. It isn't a battery, not really, but you can feel the intent order reaching beyond position into polarity. Ice 12 tells another story. Shock its sudden pressure at low temperature and it freezes into a metastable form, caught mid-step, locked into a structure it wouldn't have chosen if given time. Even ice can be surprised. These odd ices are not just curios pressed into a cabinet. They help us imagine the insides of worlds, how oceans freeze from the bottom up under a planet's weight, how heat moves, what kinds of cracks or plumes might rise. They stretch our sense of hydrogen bonding, the gentle handshake at the heart of water's personality and much of life's chemistry. The way a lattice is chosen or refused can affect strength, transport, and even how electricity trickles through a material. Structure is never only sculpture, it's function, whispering in geometry's ear. And yet, for all their strangeness, even the wildest of water's crystals look straight forward beside what happens when you try to make helium hold still. Helium is the lightest noble gas, shy, smooth, impossible to pin down. At room temperature it drifts. Cool it, and it becomes a liquid, but a liquid that refuses ordinary citizenship in the solid world. Even close to absolute zero, helium will not freeze at normal pressure. To force it into a lattice, you must lean hard, tens of thousands of atmospheres hard. It's like asking a relaxed cat to stand at attention. The request is clear. The response is a tolerant blink. Solid helium does exist, but it comes reluctantly, and keeping it there takes effort. When it does settle into a crystal, the atoms still move with unusual ease. Quantum effects sit on the throne. Helium atoms are so light, and their zero-point motion, their irreducible quantum jitter, even at the deepest cold, is so large that they resist being trapped. They can even tunnel, slipping from one position to another without climbing over the usual energy hill. This is why helium was once at the center of bold claims about supersolidity, a state where a solid would flow like a superfluid while keeping its lattice. The loudest announcements have since been softened, reinterpreted, or withdrawn, but the lesson remains: helium's crystal is no ordinary winter. It is a chorus of wave functions wearing the costume of a solid. That refusal to freeze without pressure is the purest illustration of zero-point energy you could ask for. Even at temperatures where motion should be quiet, helium's baseline shiver is strong enough to blur the positions the lattice asks it to keep. Imagine building a stack of gelatin cubes during an earthquake. The blocks slide before they can hold. Only when you press with true insistence does a structure appear, and even then, the dance continues beneath the stage. When it does freeze, helium offers a view of quantum mechanics written large enough to see by. The solid's properties are ruled by collective quantum behavior more than by the tidy picture of atoms sitting in assigned seats. It is a window, one we open in high-pressure cells and low-temperature labs, into a world where frozen means coherent as much as still. Helium is not alone in its talent for unusual crystals. Methane and ammonia, compressed in the manners we expect inside giant planets, adopt multiple arrangements of their atoms, each with different ways to carry heat or bend light. And then there is the phase with one foot on land and one in water, supersonic ice. Here, oxygen atoms lock into a crystal framework, while hydrogen ions roam through the lattice like commuters with keys, solid and liquid at once. Conductive, mobile, and ordered, this electrified crystal is a likely resident of the hot, high-pressure interiors of Neptune and Uranus, where it could help shape magnetic fields that tilt and wobble in ways that have puzzled us for decades. A material undecided, and therefore adapted stable backbone, flowing charge. That all of this grows from water's simple shape: two hydrogens, one oxygen, a slight bend, a small electric dipole feels like a magic trick performed in the open. But the trick isn't hiding, it's hydrogen bonding. The bond is gentle, compared with the covalent glue that binds atoms into a molecule, but persistent and directional, a soft hinge that can lock or give depending on crowding and heat. With it, water builds airy hexagons that float, tight frameworks that sink, cages that trap gas molecules into clathrates, and even amorphous forms where the pattern dissolves into a frozen glass. Change the pressure, ease the temperature, and the molecules negotiate anew. To study ice is to learn how matter chooses under pressure, how energy writes structure, how even the most familiar thing contains multitudes. Ice is not passive, it is political in a molecular way, forming coalitions, revising them, agreeing on orientations, changing its vote with time or stress. Solid is not the end of a conversation. It is a room where many meetings can happen. And helium, playful, unwilling helium, reminds us that freezing is not a universal law. There are substances that would rather keep moving unless the world presses very hard. A snowflake is one answer to a question water is always being asked. There are stranger answers: plates and cages, wires of oxygen with currents of hydrogen, glasses that hold no repeating motif. All they ask from us is patience and a willingness to see past the first gleam. Now let your attention drift out of the kitchen and away from the bench top into the long dark between stars. There, matter takes on habits that do not resemble our shelves and sidewalks. No polished stones, No tidy slabs of ice, no bubbling pots. The universe keeps its ingredients thin and stretched. Gas soft as breath, plasma alive with charge, dust like ancient soot, and grains of frost layered molecule by molecule on drifting specks. This is the interstellar medium, and though its density is so low, you could fit only a few atoms into the volume of your living room. It is busy. Winds, shocks, ultraviolet light, magnetic fields, and turbulence, all tugging at once. Hydrogen dominates. Sometimes it floats as separate atoms. Sometimes it pairs into molecules where shielding permits. Often, it is stripped into ions by starlight's harder shades. Once ionized, gas becomes plasma and inherits a new grammar. Charged particles feel electromagnetic fields. They gather into filaments, surf waves, and carve bubbles. They shape and are shaped by magnetic lines that twist, reconnect, and fling energy outward. If neutral gas is a cloud, plasma is the lightning within it. Not everything out there is hot. In the deep, dark cradles of molecular clouds, temperatures fall to around 10 kelvins, or even a shade lower. There, the dust grains of silicate and carbon, flecked with ice, does quiet work. It shields, cools, and provides surfaces where molecules can form. Thin films of interstellar ice grow on those grains. Not only water, but methane, ammonia, formaldehyde, and more. And under ultraviolet light, they undergo chemistry that can build larger organic molecules, the kind you'd want around when planets are forming. When a young star wakes and warms its nursery, those ices sublimate. Their chemistry joins the gas and the richness spreads. In other pockets, plasma glows at 1,000,000 degrees, but feels like nothing on the skin because there is hardly any skin to feel it with. Temperature in space means average particle energy, not warmth you could cup in your hands. A hot, thin plasma can be all energy and no hospitality. You could freeze among the heat. Elsewhere, in bulk globules, dark beads against bright nebulae, the gas is shielded and cold, ready to fall together. Gravity gathers, clumps form, pressure rises, and in a slow swell that feels like breath stretched across eons, fusion begins and light returns. Starbirth is a phase transition told in quiet patience. Between galaxies, the intergalactic medium holds a still thinner plasma, heated by shocks and time, traced in X-rays, and by the way it nibbles at the spectra of distant quasars. Even the emptiest places are not empty. They are simply sparse, and sparse is enough to carry history when the distances are large and the clocks are slow. Cosmic rays thread through these scenes, high-energy protons and nuclei running near the speed limit. They split molecules, seed reactions, and stir chemistry where sunlight is scarce. The result is not one phase or another, but a landscape of overlapping habits. Neutral gas alongside ionized rims, cold cores wrapped in warm envelopes, magnetic fields cutting across flows, and dust that tells stories in infrared light. The rules are the same as in our labs, but the stage is bigger and the timing is different. All of this is a way of saying that matter's states are not boxes, but tendencies made real by context. Ice chooses from many lattices. Helium refuses until pressed. Gas becomes plasma and learns to braid. Dust grows films and becomes an alchemist in the dark. A cloud holds a star like a breath. We know solids and liquids and gases and plasmas. We have met superfluids and condensates. We are learning the steps of supersolids, superionic crystals, and topological phases where protection comes from a knot instead of a wall. and still the list feels like a first draft. It is not hard to believe we are missing families of behavior, a phase that requires the gravity of a collapsed star, a lattice that forms only in the crush of a giant planet, a rhythm that appears in quantum systems we have not yet learned to cool or kick in the right pattern. Some might sit in data we've already taken, hiding in the averages. Some may be waiting at the edges of machines we are still building. The universe is generous with possibilities when the knobs are turned far enough. If that feels like too many doors at once, come back to a single snowflake settling on a glove. In that small, hexagonal calm is the hint of 19 cousins and more besides. In helium's reluctance is the whisper that even solid can be a negotiation. In the thin films on a dust, grain is a chemistry lesson written for planets. In a cloud's darkness is a star, and in a star's wind is the plasma that will light another sky. Matter has 1,000 ways to be itself. We have learned the names of a few. The rest are there, quiet and patient, waiting for pressure, for time, for a curious hand on the right dial. Begin with a shy troublemaker from the flatlands, onions. Most of what we touch is built from two well-behaved kinds of particles, fermions and bosons, with rules that feel tidy. Swap two fermions, like electrons, and the shared wave whispers minus. Swap two bosons, like photons, and nothing changes. In 2 dimensions, though, the rules loosen their tie. Anyons slip in and keep track of the path you make them take, trade their places, and the wave function doesn't simply stay or flip. It picks up a twist, a phase that remembers the braid you drew in space and time. It's as if the particle wears a ribbon that knots itself with every exchange and refuses to forget. That memory is more than a party trick. If information could live in the braid itself, in how world lines loop, intertwine, and come back, then small imperfections might not matter much. Tug a little, the knot remains. This is the promise behind topological qubits. You don't store a 0 or 1 in a fragile local state. You store it in a pattern that only a true untying can undo. Anyons aren't hiding in your teacup. They show up in special places where electrons flatten into a sheet, the temperature falls, and a strong magnetic field shepherds behavior into clean lanes. In those fractional quantum Hall states, the electron sea organizes so that its disturbances behave like particles with 1/3 of an electron's charge. Not new fundamental beings, but honest emergent ones, quasi-particles born of many acting as one. That too is a theme. Matter is not only ingredients, it is choreography. Step deeper, and the floor changes. Imagine regular matter, protons and neutrons, made of up and down quarks, pressed until its familiar identity blurs. Add another flavor, the strange quark, and columns of possibility open. Strange matter is the idea that under enormous pressure, a soup of up, down, and strange quarks might be more stable than the nuclei we know. Where would nature try this recipe? In the hearts of neutron stars, where a mountain's worth of mass is squeezed into a spoonful, where pressure negotiates differently with a strong force. If such a conversion holds, a neutron star might pass a threshold and become a strange star. Not neutrons packed to the ceiling, but quark matter pooling as if the constituents of protons and neutrons had been poured into a common bowl. The thought experiment runs farther. If strange matter is truly more stable, then a speck adrift in space, a strangelet, could, on contact, persuade ordinary nuclei to join and become more strange matter. a doomsday seed that turns what it touches into itself. It's a shiver of a story, and there is no evidence the universe is quietly doing this to us. But the idea keeps one door open. Stability may have levels we haven't climbed to yet, phases where settled looks different than it does in our temperate, low-pressure corner. Somewhere between neutron stars and black holes is another possible room, the quark star. Compress a neutron star further, not enough to collapse space-time itself, but enough to deconfine quarks over a macroscopic volume, and you might get an object made not of neutrons, but of unbound quark matter. It would be an entire body, living in a phase we have only sketched in equations and glimpsed for micro-instants in colliders. Astronomers watch for clues on usually small, heavy stars, sudden changes in pulsar timing, bursts that don't quite fit our models. Confirmation would tell us that a whole astrophysical personality exists beyond the solids, liquids, and plasmas we cradle on Earth. If we allow ourselves one more soft speculation, turn to the matter we cannot see, the dark kind. We know it by its gravity, by the way galaxies spin and the way clusters lens distant light. We do not know its makeup. Candidates range from heavy, shy particles to feathery axions, whose presence feels more like a background hum. But what if dark matter is not just lonely particles? What if it has its own forces, its own electromagnetism in a mirror key, its own bound states? Dark atoms, dark molecules, dark crystals, entire topographies of phase behavior unfolding in silence beside our luminous world. If that were true, the universe would carry a hidden geology, rich with transitions and textures that barely brush ours. We would find it not with a microscope, but by inference, subtle patterns in the cosmic microwave background, faint anomalies in lensing, the softest hands of underground detectors catching a rare tap in the dark. Even in the matter we can touch, the map is unfinished. We used to think a list would do solid, liquid, gas, plasma, and then we met superfluids and condensates, supersolids and time crystals, topological insulators with edges that sing while their middles stay hushed. Again and again, new behavior arrives when we cool further, squeeze harder, purify more carefully, or drive a system with a rhythm that opens a new door. The reason is simple and deep. Matter is made of relationships. It's not only which particles are present, but how they talk, how they align, entangle, and agree on patterns that are not obvious from the parts alone. The recipe matters. So do timing, symmetry, and small, quiet imperfections that, paradoxically, protect rather than break. Quantum devices push us into these delicate neighborhoods on purpose. We cool to slowness, polish away disorder, and use light like a gentle hand to move states along a chosen path. In that calm, phases appear that would be impossible in the bustle of room temperature. Maybe, in those near-silent laboratories, we'll nudge into quantum liquids or entangled lattices we haven't named yet. The history of physics is a sequence of surprise smiles. Every time we declare the catalog complete, nature adds a chapter with an ending we didn't expect. Push further, and the ground itself begins to shift under the question, what is a phase? In the classical world, the answer feels solid. Look at structure, compressibility, heat capacity. Declare solid, liquid, gas. In the quantum world, a system can be a cloud of possibilities until a measurement leans in. The act of checking can be part of the definition. That doesn't mean reality waits on us to exist. It means some identities show themselves only through particular interactions. Phase can be contextual, emergent, delicate, tied to the way a system is allowed to evolve and the symmetries that hold while it does. Consider quantum phase transitions. They don't care about melting points or boiling points. They live at absolute zero, where heat sits down and quantum fluctuations keep pacing. Turn a knob, magnetic field, pressure, interaction strength, and the ground state reorganizes. No thermal jostling, just a change in the rulebook the system is playing by. The distinction between phases here might not be in atom positions, but in invisible orders, whether spins are entangled in a pattern you cannot see directly, whether a topological invariant, the kind that counts holes rather than bricks, has changed its value. Two materials could look identical under a polite glance and still live in different phases, separable only by how their edges conduct, or by the phase their wave functions pick up when braided around a defect. Symmetry-protected topological phases make the point gently. They are distinct as long as certain symmetries' time reversal, say, or particle hole, remain unbroken. Break the symmetry, and the difference between phases can melt away without any dramatic fracture. The phase is real, but conditional. It is a snowflake that keeps its lace as long as the light is cold and quiet. There are stranger courtesies in this landscape. The quantum Zeno effect shows that frequent observation can hold a system still, freezing its evolution by constantly asking it who it is. Peak often enough, and the transition you expected will not occur. The system keeps resetting to who it was when you last asked. In delicate, driven settings, that kind of measurement back action can shape the energy landscape itself, nudging a system to stay on one side of a dividing line that, unobserved, it might have crossed. Observation doesn't conjure phases, but it can shepherd a system into or away from behaviors as if attention were a mild magnetic field. Entanglement pushes the definition further still. It links many body systems in ways that ordinary measurements of density or simple correlations cannot capture. In some phases, the structure of entanglement, the way information is shared non-locally, is the order. That order hides from microscopes and reveals itself in responses, in how the system carries heat along an edge, but not through its heart, in how defects behave when braided, in the low-lying excitations that appear not in bulk spectra, but at boundaries. It's like walking into a quiet room and sensing harmony before you can name the instruments. All of this sounds abstract until you remember we use it. We coax time crystalline rhythms out of qubit arrays by kicking them just right and letting many-body localization keep the beat from dissolving into heat. We protect edge currents with topology so small scratches can't scatter them away. We design materials whose flexibility changes with the pace of your touch, then fold them into helmets and suits. We tune ultra-cold gases until their wave functions overlap, and the many becomes one for a moment long enough to draw interference fringes you can photograph. The poetry of phases is not an escape from the world. It's the world seen with patience. Return for a breath to the speculative. Dark matter with its own chemistry. Strange stars humming in a key our eyes can't hear. Anionic braids tying memory into knots. Phases defined by entanglement rather than arrangement. Perhaps some of these are wrong turns. Perhaps others are already present in the data, shy and waiting for the right question. The larger point is soft and steady. Phase is not only a label, it is a way matter chooses to be when conditions, symmetries, and conversations line up. Sometimes the conversation includes us. So the next time you watch cream spiral into coffee, think of braids and memory. when frost feathers a window. Imagine oxygen lattices sliding into new blueprints under pressure and cold you cannot feel. If a screen dims, picture rod-shaped molecules turning in unison, like tiny compass needles. When a headline mentions a neutron star with a mass too heavy for comfort, imagine quarks deciding to pool. And when a physicist says they've made a system that ticks in its ground state, remember that rhythm can be order. Are we missing phases? Almost certainly. Are they strange? Without apology. But the strangeness is generous. It widens the map without tearing it, shows that matter is less a cabinet of samples and more a library of behaviors. Some volumes sit on low shelves: ice, water, steam. Others are bound in dark cloth and whisper of braids, of knots, of coherence born in the cold and liquid born in the hottest heat. We will keep reading. We will keep cooling, squeezing, and listening. And in that quiet work, more states of matter will reveal themselves not as exceptions, but as natural sentences in the language the universe has been speaking all along. What is a state, really? Is it something that exists on its own, quiet, complete, waiting to be found, or something that condenses from possibility when we look closely enough? Different schools of quantum thought offer different lanterns for the same fog. One says a system has no single set of properties until a measurement settles them. Another says every outcome happens somewhere, and we just walk the branch that fits our footsteps. A third suggests a hidden current beneath the surface, a smooth pilot wave steering the dance. They disagree on metaphors, but they share a simple insistence. Observation isn't a shrug, it's an interaction. It moves the air. Sometimes it writes the script. Follow that thought into phases of matter, and the ground softens in a welcome way. If measurement is part of the stage, then phases are, at least a little, about context. The way we nudge, the way we watch, the way a system is allowed to breathe, all of it shapes what we see. That doesn't mean reality is slippery in a careless sense. It means it's participatory. The world answers the questions we ask in the language of the question. In the quiet rooms where quantum simulators hum and cold atom traps glow faintly, you can feel this principle at work. There, researchers build materials out of light and magnetism, artificial crystals with tunable geometry, gases cooled to a stillness where individual atoms blur into collective waves. Change the probe, and the system shows a different facet. Entangle one patch with another, and you can stabilize patterns that didn't exist a moment before. The behavior is real, not because it lasts forever, but because it obeys rules while it lasts. It's not a trick, it's physics at that lovely edge where equations meet choice. Under this lamp, the words phase, state, and system loosen their collars. Matter looks less like a noun and more like a verb. The identity of a phase is something a system does when certain symmetries hold, when certain kinds of noise are hushed, when certain nudges are allowed and others are refused. Our role is not to command, but to set conditions with care, to listen for the answers that arrive when the room is quiet enough. And yet, even here, nothing is anything you want. Superfluids still obey the strange courtesy of flowing without friction but not without rules. Time crystals still tick with a rhythm protected by structure, not by fantasy. Topological edges still carry current, while the interior remains shy. Plasma still bows to fields. The truth beneath the softness is not that anything goes, but that context matters, and that context can be crafted gently. It's hard not to notice the echo with our ordinary lives. Emotions, identities, relationships, they too can be stable and conditional at once, depending on the light, depending on the company, depending on what is asked and what is left to rest. They unfold into different shapes without becoming untrue. Perhaps it's no accident that matter at its smallest listens in a similar way. The universe may favor a kind of grace, structure when needed, flexibility when allowed. So when we name phases, we're not collecting stamps, we're learning a language, the ways structure, interaction, and perception braid together. It's the outline of a conversation between what is, what could be, and what our questions invite. That's why quantum physics feels almost poetic when approached slowly. Not because it's vague, but because it's layered. Certainty and mystery sit side by side without argument. A theorem shares the table with a question mark, and both are fed. Change, after all, is the quiet current beneath everything. Tea boils, iron rusts, a snowflake loosens and becomes a drop. A star spends its balance and folds inward. Shifts grand and miniature never stop passing through the world. We feel it in our hands when ice fades into water. We smell it when rain turns to steam on a hot road. Even before the dramatic edges melting, boiling, condensing, there are the in-betweens. A glass, relaxing over decades. A polymer, stretching and then remembering itself. A membrane becoming more fluid as a cell cools and warms with the hour. Think of the classic rise from solid to liquid. In a crystal, atoms keep to a choreography neighbors recognized, distances kept, a pattern repeated across space. Warm the lattice and the dancers press against their steps. The binding still holds, but the room is louder. A little more heat and the pattern lets go. Not failure change. The parts keep company without fixed partners. A liquid keeps nearness without the leash. It flows. It finds the shape of its cup. Turn the dial again, and the distance grows. The music changes key. A gas becomes a freedom of paths, collisions, and glances, setting the only schedule. Turn the dial back, and the story retraces itself. Vapor condenses on a mirror cloud from breath translated into a million tiny drops. Dew carpets morning grass. Fog gathers and then thins. The borderlands have their own delights. Sublimation, where a solid becomes a gas without a stopover in liquid. Deposition, where frost writes lace directly from the air. Triple points, where all three phases share a precise piece. These aren't lines as much as riverbanks, edges that wander with pressure and temperature until you learn their habits. If you linger, you start to notice how slow changes carry equal weight. Rocks on human timescales are stubborn. On planetary clocks they flow. The mantle creeps. Glaciers slide. Steel stretches and contracts with the seasons like a city taking long breaths. In laboratories, we find phases driven not by heat at all, but by deeper levers, magnetic fields that re-script a ground state, interactions tuned until a collection of particles elects a new order. Symmetry-protected distinctions that vanish the moment a particular mirror breaks. At absolute zero, where thermal noise sits down, a system can still change its mind when a hidden parameter crosses a quiet threshold. That's what we call a quantum phase transition. Nothing boils, everything shifts. And then there is the way looking itself can shape what's possible. Ask too often and you can pin a system in place. The quantum Zeno effect, holding evolution at the threshold like a baker who keeps opening the oven. Measure at the edges, and the hidden pattern reveals itself in conductance. Measure in the middle, and the same system looks plain. Sometimes the order parameter is not a density or a magnetization, but a topological count, or a particular twist in entanglement, the part of the story you can only hear by listening for a specific harmony. If this feels a hair abstract, bring it home again. Watch cream bloom in coffee. See the spirals and braids. That's mixing, yes, but also a reminder that paths matter, how one thing winds through another. Watch frost draw ferns. That's deposition obeying rules you can't see. Look at a screen and imagine the small rod-shaped molecules turning together in each pixel so a letter can stand up in light. Lift an ice cube to the window and remember there are 19 cousins and more waiting for pressure to teach them a new posture. None of this is myth. It is the patient way matter expresses possibility. Some of what we've touched lives at the edges of what we can make. Superfluids gliding, supersolids holding and flowing at once, quark liquids born in a collider's blink, time crystals keeping a rhythm that ordinary systems lose, phases defined not by pattern in space, but by pattern in how wave functions pick up phase when braided. Some lives in the sky, plasma riding auroras, ice that forms in high-pressure mantles, dust that grows films of organic ice in the cold of interstellar clouds. Some lives on a kitchen shelf, ketchup yielding, oobleck hardening under your hand, glass that rings like a solid and dreams like an unfinished liquid. We started with a question, and it keeps widening. What counts as a state? Maybe the gentlest answer is this: a state is a way matter behaves when its conditions, connections, and symmetries line up. It's less a box than a song. Some songs are loud and obvious, some are soft and require you to lean in. Some last an eye blink, some play for eons, some appear only when the audience stays very still. And because we are part of the room, because our questions, our apparatus, our patience, and our care all change the air, there are times when the song includes us in its timekeeping. None of this means the world is a whim. It means the world is generous. Our lists, solid, liquid, gas, plasma, are not wrong. They're foundations. On that base, other floors rise. Super strange, topological, time-kept, ion-led. We climb as far as our tools and our curiosity allow, and each landing has a view the last did not. The names, too superfluid, time crystal, strange, carry a touch of poetry because the phenomena themselves demand it. Precision and wonder draw breath from the same lungs. If you like, try holding one more echo for yourself. We, too, are not fixed. We have phases that arrive with the season, with a sentence, with a quiet hand on the shoulder. We can be structured, we can be fluid, we can be somewhere in between, and we can change with a threshold crossed softly at midnight. That isn't failure, it's how a heart keeps time. So here, at the edge of the lamp's circle, let the ideas dim to embers. The room looks still, but it never is. Atoms hum in your blanket. The air trades tiny warmths with your skin. Somewhere a glacier inches. Somewhere a cloud collapses into a star. Somewhere a lab lowers the last bit of noise, and a condensate forms like a long-held note. Everything is always becoming. That's not a threat, it's a lullaby. Set your shoulders down. Loosen your jaw. Feel your breath arrive and go, like a tide that knows the shore by heart. The universe will keep rewriting itself at a pace that asks nothing of you tonight. You can let it. Let the small motions carry on in the dark, gentle and exact. If sleep wants you, you don't have to reach. Close your eyes. The story keeps telling itself whether or not you're listening, and in the morning, it will still be here, quiet, patient, and warm.